Okay, so let's start today's class. Today we will be, as I said, today we will be solving problems based on analog communication week 5, lectures 19 to 14, which are on single sideband suppressed carrier and vestigial sideband suppressed carrier. So, yeah, previously what we have done is double sideband full carrier and double sideband suppressed carrier. So in double sideband suppressed carrier we have upper sideband, we have lower sideband, and we do not have any carrier component. But in double sideband full carrier we have upper sideband, lower sideband, as well as the carrier signal. So first thing, but in single sideband suppressed carrier, in single sideband suppressed carrier, we only have one of lower sideband or upper sideband, and any we don't even have any carrier. So just one lower sideband or upper sideband, only one of them. Okay, so like this. What is DSBSC? DSBSC is like this. Okay, so here we have like mirror images. This is like the lower sideband. This is called the LSB, and this is the USB. But in single sideband suppressed carrier, this is the SSBSC. Sorry, this is the DSBSC. Beg your pardon. This is the DSBSC. For SSBSC, only one, say the lower sideband is present. So, if this is the FC, carrier frequency, so the carrier is suppressed, only the lower sideband is present. FC. Okay, and this is FC minus FL. Corresponding mirror image will be in the negative domain. Corresponding negative image will be in negative domain. So this is minus FC, this is FL, okay, and this is FC. So FC minus FL, where FL is the lower sideband frequency. Now, envelope detection based modulation scheme does not require carrier recovery. So this is the first question, that envelope detection based modulation scheme does not need carrier recovery. So what is an envelope based detection scheme? This is the first question. Okay. So what first question is, envelope based detection scheme does not require the knowledge of carrier. So in an envelope based detection scheme you have something like this. So the amplitude is varying. Okay. So in envelope based detection scheme, the main message signal is encoded in this envelope, the change of amplitude. Okay. So this change of amplitude, this is called the envelope. Envelope. Similarly, there will be an envelope here also, which will be the mirror image of this envelope. Now this envelope is contains the message signal. So we only need the amplitude of the carrier change in the amplitude of the carrier signal. We don't care about the absolute value of the amplitude of the carrier signal, nor do we care about the frequency of the carrier signal. So we don't need to know about the carrier exactly to know about the envelope. The envelope can be detected by the change in the carrier amplitude. So thus this is a true statement that we do not need carrier recovery. So the correct answer is 1A, true, is the correct answer. So we do not need any carrier recovery. Going to the next question. SSBSC requires the message signal to have magnitude 0 at 0 frequency. Okay, so that means SSB-SC signal requires to have the message signal to have a magnitude of 0 at 0 frequency. What is 0 frequency, otherwise known as zero frequency, is also known as DC. So what it says is that the message signal must have DC for single sideband suppressed carrier modulation. Now to better understand this, we need to get the formula of single sideband suppressed carrier. Okay, so we need to write the expression for single sideband suppressed carrier, which is given as SSBSC. Let's consider we are taking the lower sideband. Okay, so SSBSC for lower sideband. For lower sideband, the SSBSC signal is given as AMAC by 2 cos 2 pi FC minus Fn T. Now as you can see this okay, so for the SSB-SC modulation, the graph will look something like this. It will only have this sideband, and clearly you can see that in the frequency component here we do not need any DC component here. This is the DC, sorry, this is FC and this is some FC minus FL, where FL is like the half bandwidth of the band. So we do not need any kind of signal here. If we had any kind of response here, so we will not have suppressed carrier. We will have something which has a component. So we cannot have anything here. So this should be 0. We only have everything purely in the sideband for SSBSC. So the correct answer is that it requires 0 signal to have magnitude of 0 at 0 frequency. So DC should be 0. So this is again true. Now going to question 3. SSBSC is the most bandwidth inefficient in AM. Now bandwidth inefficient means power per unit bandwidth is low. Okay, so here we can see that whatever information per unit bandwidth is low. Now in DSB, whatever information we were sending in DSB, we were sending across 2 bands. So if say this band is around FL in width, so and this bandwidth is FU. So FC plus FU and FC minus FL. So here the bandwidth is FC plus FU minus FC minus FL. So FU plus FL. This is the bandwidth that is equal. But same information in a, this is for DSBSC. For DSBSC. But the same information you can send via SSBSC. And you will need only half as much bandwidth. Just FC. This is FC minus FL. So the bandwidth you need is FL. FC minus FL. So FL. So you require much less bandwidth to transmit the same information. Thus, SSBSC is more efficient. Is more bandwidth efficient because you need less bandwidth to transmit the same information. That is the main advantage of SSCSC. SSCSC is more bandwidth efficient. So if SSCSC is more bandwidth efficient, then the statement that SSBSC is the most bandwidth efficient in AM is clearly false. So the correct answer is false. Okay. Okay. So question number 4. Now let's move to question number 4. For the Hilbert transformation MHT of the following signal MT equal to cos omega naught t cos omega 1t, assume omega naught greater than omega 1t. So what is the Hilbert transform of this thing? So find the Hilbert transform of this signal cos omega naught t cos omega 1t. MT equal to cos omega naught t cos omega 1t. Now you can do it in two ways. One is simply using the Hilbert transformation integration formula and putting this value and doing the transformation. Or what you can see is for sinusoids, Hilbert transformation is nothing but a phase shift by pi by 2. Okay, for sinusoid signals, Hilbert transformation is nothing but phase shift by pi by 2. So what is Hilbert transformation? Hilbert transformation here is empty convolution 1 by pi t. Okay, but we don't need to solve this integration because for sinusoids Hilbert transform amounts to a phase shift by pi by 2. So let's expand MT. MT is cos omega naught t omega 1t. So we can write it as half into 2 cos omega naught t omega 1t. Now we can use trigonometric formulas. So cos omega naught t cos omega 2 cos a cos b, that is cos a plus b plus cos a minus b. So cos omega naught plus omega 1 t plus cos omega naught minus omega 1 t. Now this thing is cos omega naught plus omega 1 t cos omega naught minus omega 1 t. Now following a Hilbert transform MHT is simply a pi by 2 transformation, a phase shift by pi by 2. So when you phase shift cos by pi by 2, you get sine. So sine omega naught plus omega 1 t plus sine omega naught minus omega 1 t. So this is sine omega naught plus omega. Now let's use another trigonometric formula here. Okay. So MHT we have guessed half sine omega naught t, omega naught plus omega 1 plus sine omega naught minus omega 1. So if you expand sine omega naught cos omega 1 t plus sine omega naught cos omega naught sine omega 1 t. Sine a plus b is sine a cos b plus cos a sine b, and sine a minus b is sine a cos b minus cos a sine b. So finally you will get 2 sine a cos b. So MHT is half into 2 cos a sine 2 cos a sine b. So cos omega naught t plus into sine omega naught t. So this is cos omega naught sine omega 1. Okay, I have actually used the formula in the opposite way. So it's not cos omega naught sine omega 1. This will be sine omega naught cos omega 1. Opposite. I have used the formula in an opposite way. Sorry for that. Okay, so finally the answer will be 2 sine omega half and 2 will cancel. So it will be sine omega naught cos omega 1 t. So answer C. Option C. Sine omega naught cos omega 1 t. So this will be option C. Now going to question number 5. A single sideband signal is generated by modulating signal of 1000 kHz carrier by the signal mt equal to cos 2000 pi t plus 2 sin 2000 pi t. The amplitude of the carrier is AC equal to 500. Okay, so we have a carrier modulating signal of 1000 kHz carrier. Acha, is 1000 kHz carrier. We have a 1000 kHz 500 amplitude carrier, and we have a message signal as cos 2000 pi t plus 2 sin 2000 pi t. So the message signal is, let's go to question number 5. Okay, the message signal is cos 2000 plus 2 sin 2000. Mt equal to, yeah. Now the carrier signal is given as 500 amplitude of 500. The carrier signal frequency is not given. Okay, the modulating signal of 1000 kilohertz. So the modulating signal has a frequency of 1000 kilohertz, as can be shown in cos 2050. Now we have to find the lower expression of the lower sideband. So we have to find the expression of the lower sideband using we are using SSBSC. So for SSBSC, AM sorry XLSBT, where XLSBT is the expression for the lower sideband, is AC MT cos 2 pi FCT plus MHT sin 2 pi FCT. Let's check whether the sin cos placements are correct. So it is MT cos 2 pi FCT plus MHT sin 2 pi FCT. Okay. Now we have to find the MH. As we have said, for sinusoids, Hilbert transform is equivalent to phase shift by pi by 2. So your MT is cos 2000 pi t plus 2 sin 2000 pi t. So what will be MHT? MHT will be cos 2000 pi t, we add up pi by 2, sin 2000 pi t. When we are adding pi by 2, it's going to the second quadrant. But in second quadrant, sine is all sine tan cos. So sine is positive. So this will be sine 2000 pi t. But in the second quadrant, cos is negative. So minus 2 cos 2000 pi t. So it will be sine 2000 pi t minus 2 cos 2000 pi t. So this is the Hilbert transform. Once we have the Hilbert transform, we can write this lower sideband expression as 500 cos 2000 pi t plus 2 sin 2000 pi t. This will be multiplied by cos 2 pi fct, which we do not know, plus mht. So sin 2000 pi t minus 2 cos 2000 pi t this will get multiplied with sin 2 pi fct. Okay, now once that is done, you multiply. So we have cos 2000 pi t cos 2 pi fct. We have cos, sin cos, and we have sin and cos sin. So we have 4 different terms. We will collect cos and sin because they will together. Cos A cos B plus minus sin A sin B will be cos A minus B. So sorry, it will be cos A plus B. So cos 2000 pi t cos 2 pi fct plus sin 2000 pi t sin 2 pi fct. This is one expression. So this expression is done. Next, we have a 2 common sine 2000. Let's take minus 2 common and bring this second term first. So cos 2000 pi t, sorry, sin 2 pi fct cos 2000 pi t. We are bringing the second term first. Cos 2000 pi t minus the first term, that is cos 2 pi fct sin 2000 pi t. We simply recollected the terms. Now, the first pair of terms, cos 2000 pi t cos 2 pi fct plus sin 2000 pi t sin 2 pi fct, this evaluates to, what does this evaluate to? This evaluates to cos a minus b. So 500 cos 2 pi fct minus 2000 pi t. And sin 2 pi fct cos 2000 pi t minus sin cos 2 pi fct sin 2000 pi t. So this will be sin a minus b. So we are done. Now let's check for answer. 500 cos 2 pi fc minus 1000. So 2 pi, this one minus it's 200 sin 2 pi fc minus 1000. So it will be, correct answer will be C. So the correct answer will be C. We have also got cos a minus b minus 2 sin a minus b. Option C. Cos a minus b minus 2 sin a minus b. Now, question number 6. If a message MT with bandwidth B is modulated with a carrier frequency FC with FC much greater than B, to form a VSB signal, this modulated signal is passed through a high pass filter with maximum gain 1 and slope alpha. So in VSB signal, we do not even allow the full sideband. We allow a vestige of the sideband or a fraction of the sideband. So it is even more bandwidth efficient than single sideband modulation. So if a message MT with bandwidth B is modulated with a carrier frequency FC with FC much greater than B, to form a VSB signal, this modulated signal is passed through a high pass filter with maximum gain 1 and slope alpha. Find out the excess bandwidth it requires as compared to its SSB modulated counterpart. So, in SSB modulated signal, we allow the whole sideband, whereas in VSB we allow only one sideband and a part of another sideband. So it is not as bandwidth efficient as SSB, but SSB sometimes may not be sufficient. Sometimes to represent the data, SSB may not be sufficient, but double sideband suppressed carrier DSB might be too much. So there might be cases where we need 1.2 sidebands, not one but not two either. we need say 1.2 sidebands or 1.7 sidebands. So how do we implement that? We of course do not want the whole two sidebands because that will be bandwidth inefficient. So what we will do is we will pass this signal. We will pass this signal with through a filter. Now this filter will have a roll off. So this roll off will finally die down at a certain after a certain frequency. Huh. So once this dies down, we will only have this portion from this portion as an excess, as a vestigial segment. So if we need some extra bandwidth, what I mean to say is it will have some extra bandwidth, but not as much as full double segment. So here we have single sideband. Single sideband is something like this, SSB, and DSB is something like this. This is SSB, and DSB is something like this. So what is vestigial sideband? In vestigial sideband, we don't take the whole double sideband, but we don't take only one band either. We take one, and then maybe this much. So this is a vestigial sideband. So we have one sideband and one vestige. This is called a vestige, one portion of another sideband. Okay. So to implement this, we need to cut this sideband before it before the frequency, like before the frequency finishes. We need to cut this sideband. Okay, so now in this question they are saying that what to find out the excess bandwidth it requires as compared to SSB modulated counterpart. So if we have this slope, then in from Fc plus delta F to Fc minus delta F, we have a slope of alpha. Thus, in this 2 delta F bandwidth, we get a slope of alpha. What is the curve? Let's find out the value of this alpha. See, the curve is something like this. Within this 2 delta F, we start with 1. They have said that the gain is 1. Now, within this 2 delta F region, from Fc plus delta F to Fc minus delta F, this is Fc minus delta F, and this is Fc plus delta F. In this 2 delta F region, this 2 delta F region, okay, in this 2 delta F region, this goes from slope 1 to 0. So what is the slope? The slope is change in y by change in x. So 1 minus 0 is the change in y, and what is the change in x? From Fc plus delta F to Fc minus delta F. That is 2 delta F. So it is 1 by 2 into delta F. But the slope is given as alpha. Therefore, alpha equal to 1 by 2 delta F implies the excess bandwidth. So where is Fc? Fc is here, right? So what is the excess bandwidth? Excess bandwidth is this much. This is the excess bandwidth. So excess bandwidth is delta f. So it will be 1 by 2 alpha. Okay. Alpha equal to 1 by 2 delta f or delta f equal to 1 by 2 alpha. So the correct answer is option C, 1 by 2 alpha. Option C. Now let's go to question 7. Consider the following baseband signal. Figure is given below. So 0.3 to 0.4 there is a triangle. Okay. Consider with the minimum and maximum frequencies of 0.3 kilohertz and 0.4. The signal is modulated with center frequency 10 kilohertz. Find the minimum and maximum bandwidths of the filter that can be used to perfectly construct the LSB, SSB or the lower sideband modulated signal. So this signal is modulated with center frequency 10 kilohertz. So the signal is given like this. It's a triangular curve. From 0.3 to 0.4. Now this is from 0.3 to 0.4. Now it is modulated with a maximum frequency, center frequency of 10 kilohertz. So for amplitude modulation, whatever signal there is, it will just get repeated. So if you have a signal like this 0.3, 0.4, the lower sideband will be this and the upper sideband is 0.110.3. Okay, so the figure will be not like this. The figure will be, I think, there is another curve like this in the negative axis. Now this thing will get repeated. So this is what an amplitude modulation looks like. This center frequency will be 10 kilohertz as given in the problem. So if this is 10, what will be this? This will be 10.3 and this will be 10.4. This will be 10 minus 0.3, so this will be 9.7 and this will be 9.6. This will be minus 10. Okay, and this will be accordingly minus 9.7, minus 9.6, minus 10.3 minus 10.4. So what is the minimum cutoff of to extract? Now what is the problem? The problem is that you have to extract the bandwidth, find the minimum and maximum bandwidth of the filter that can be used to perfectly construct the lower sideband SSB. So we have to extract only the lower sideband. So the minimum filter that we need is this much. So we can have this much. This is the, let's draw the filter with red. This is the minimum cutoff. This is the minimum bandwidth filter. Minimum bandwidth. Now, what will be the maximum bandwidth? For maximum bandwidth, you can go from 0. You can take this whole thing. If you take this whole thing as your filter, if you pass this whole thing up to 9.7, you will still get only this band. But if you pass 10 kilohertz, then also you will only get this thing. But the moment you pass anything more than 10.3 kilohertz, you will get another band. So it will not be lower sideband only. So the maximum filter will be something like this. Up to here, up to 10.3. So this is the maximum bandwidth. Maximum bandwidth filter. Therefore, bandwidth minimum is 0.1 kilohertz and bandwidth max is 10.3 kilohertz. So 0.1 and 10.3. Answer is C. Now, consider the same signal shown in question 7. So we will take still the same signal. It is modulated with a carrier frequency of 2.3 kilohertz. So now the center is no longer at 10, it is at 2.3. Our objective is to form a LSB SSB signal out of this modulation using a filter, okay, with maximum gain 1 and linear roll-off alpha. So the filter, what they mean to say is we have something like this. Question 7 in question 8. Let's change the color. So we still have this kind of an expression graph, but two things have changed. First thing is the center frequency is no longer 10, it's 2.3. Okay, so there is another mirror image here with center frequency of negative 2.3. Now we have this thing. This is the first change, that the center frequency is at 2.3. So this will be at 2. Am I drawing it correctly? No, sorry. The opposite will be there. I drew the bands different. Yeah. It will be like this. And this will be 2.6, 2.7, this will be 2 and 1.9. So it's all done. Now they are saying that they have a filter, but this filter, previous filter was ideal. So now they are saying that the filter that you have is not ideal, it has a linear roll-off. So if you have a filter, let's draw the filter with red. If you have a filter, its response is something like this, ideally. But with roll-off alpha, it will be something like this. So here it is 1 and here it will be 0. So if this is fc, this will be, if the slope is alpha, so this will be fc plus 1 by alpha, because if the slope is alpha, we saw that the axis bandwidth is 1 by alpha. This changes in alpha amount of frequency, it will change from 1 to 0. So I'll say this is delta f. For clarity, let us show how this alpha is done. Say this is delta f. So what is the slope? Changing y, 1 minus 0 by changing x, delta f. So your alpha is 1 by delta f. So what will be delta f? Delta f will be 1 by alpha. So this ending point will be fc plus 1 by alpha. Okay, so this is my filter. It will not stop at the cutoff, it will stop at 1 by alpha frequency after cutoff. Now they are saying that the band 0 to 1.6 kilohertz is reserved for another purpose and the filter response should not penetrate the band. With this constraint, what could be the minimum value of alpha? So, our filter response, which is this thing, this whole thing, this thing cannot go till 1.6. So, we have to extract the lower side band, alright, but we have to make the minimum free bandwidth. We have to extract the lower side band, but it cannot go to beyond this 1.6. So normally what will we have? We have a filter like this. We will cut off this portion. What we will have is a filter like this. So it will of course be constant. It will of course pass till 1.9 because we have to get the sideband, and then it will finish at alpha. So it will start from 1.9 and it will finish at 1.9 plus 1 by alpha. Rather 1.9 minus 1 by alpha because we are going to the left. So our constant is that this 1.9 minus 1 by alpha, which is the stopping point of the filter, this should not be lesser than 1.6. So it should always be greater than or equal to 1.6. If it is less than 1.6, it will go into this forbidden band. This band is forbidden. It cannot go into this band. So 1.9 minus 1.6 implies 1.9 is greater than 1.6 plus 1 by alpha, implies 1.6 plus 1 by alpha is less than equal to 1.9, implies 1 by alpha is less than equal to 0.3, implies alpha is greater than equal to 1 by 0.3. 1 by 0.3 is 3.33, implies alpha is greater than equal to 3.3. So if alpha is greater than equal to 3.3, then what is the minimum value of alpha? 3.3. So 3.3 is the minimum value of alpha. So let's see. Yeah, the correct answer is A, option A, 3.3. So 3.3 is the minimum value of alpha. Okay, this was a nice problem. Option A, 3.3. Now, question number 9. Let's go to question number 9. Let 15 signals, each band limited to 7 kHz, are to be transmitted over a single channel. let 15 kilohertz signals yes. Sorry for the network disruption on my end. So let's resume. Let 15 signals each band limited to 7 kilohertz. Let 15 signals each band limited to 7 kilohertz to be transmitted over a single channel by frequency division multiplexing. If SSB-SC modulation is used and a guard band of 1 kilohertz is used, then the bandwidth of the so there are 15 signals, each band limited to 7 kilohertz, and we are using SSB-SC modulation. So in SSB-SC, only this 7 kilohertz band. In the DSB-SC, we have double of this 7 kilohertz bands. Whereas in SSB-SC, if this is like the original signal of 7 kilohertz, it's band limited to 7 kilohertz. So in DSB-SC, what we will have is this thing. So in effect, it will have a bandwidth of 14 kilohertz for DSB. But for SSB, it will be only 7 kilohertz. So this is FC, this is FC here. So this will only be 7 kilohertz. So if we have 15 such 7 kilohertz SSB signals, 15 SSBs, so 15 SSBs will be 15 into 7 kilohertz. Now each of them has a guard band. So there are 1 kilohertz. Okay, so there are 15 signals and each band limited to 7 kilohertz. And a guard band of 1 kilohertz is used. So if there are 15 signals, if there are 2 signals, there will be 1 guard band. If there are 3 signals, there will be 2 guard bands. So if there are 15 signals, there will be 14 guard bands. So actually the total bandwidth will be 15 into 7 plus 14. So 15 into 7 plus 14 is 119. So we will need total 119 kilohertz bandwidth. Now I don't know why they have used 11 here. It won't be 11, it will be 14. So the correct answer will be D, none of the above. Okay. So the correct answer will be D, none of the above. This might be wrong here. Now consider the QAM signal MT in question number 10 is equal to M1T cos omega t plus M2T sin omega t, with the carrier frequency omega being much higher than the bandwidths of M1T and M2T. Moreover, the power of M1T and M2T are P1 and P2 respectively. The in-phase part M1T is recovered by multiplying the signal MT with the phase imperfect carrier CT equal to cos omega t plus theta and passing through a low pass filter. Find the average output of the power of the output of the filter. Okay, so there is M1 and M2, and then there is MT, which is a QAM modulation of M1 and M2. Now they are saying M1T is recovered by multiplying MT with cos omega t plus theta and then passing through a low pass filter. So we have to find the average power of the output of the filter. Assume that M1 and M2 are chosen such that the time average of the product M1T M2T is 0. So here, what is the output that is getting fed? So we have an MT. MT is equal to M1T cos omega t Okay. Now we are saying that we multiply it with cos omega t plus theta to get the output, and then we filter it to get the output. So pre-filtering, what is the output? The output is mt into ct. So it is m1t cos omega t plus m2t sin omega t into cos omega t plus theta. So this is your input to the filter. Now this thing gets filtered. So what is the power? Now in the main thing about this filter is whatever this omega t term is, it will vanish all the omega t terms. So wherever there is omega frequency, it will just vanish that. So m1t cos omega t plus theta. So this one is m1t by 2 cos omega t plus theta. So 2 cos a cos b, which will be cos a plus b plus cos a minus b. So cos theta. Omega t plus theta minus omega t. So cos theta. And another is m2t by 2 sin omega t cos omega t plus theta. So it will be sin a 2 sin a cos b. So sin a plus b plus sin a minus b. Sin a plus b minus sin a minus b. So sin a plus b 2 omega t plus theta minus sin a minus b minus sin theta. Now filtering will remove all the 2 omega terms. So we will be left with filtering. After filtering, zt is equal to m1 t cos theta by 2 plus minus m2 t sin theta by 2. Now the power of this thing is mod zt square is equal to mod m1 t cos theta by 2 whole square. This thing will be one square term. Another square term will be m2 t sin theta and finally we will have one thing which is m1t m2t cos theta sin theta, but since the average power for this one is 0 given, so this will go to 0. So ultimately the power will be, this thing will be by 2 square by 2 square by 2 square. So ultimately power will be 1 by 4 mod m1t cos theta square plus mod m2t sin theta square. Now what is the power of m1 and m2? The power of m1 and m2 is given as p1 and p2. So we can simply write this as mod m1 square will be p2 and mod m2 square will be mod m1 square will be p1 and mod m2 square will be p2. So 1/4 p1 cos square theta plus 1/4 P2 sine square theta. Now if theta were to be 0, this second term would have vanished and first term would have been 1/4 P1. So this would have led to perfect detection. Only the M1 carrier power will be there when we are detecting M1. But since there is an imperfect phase, so there is a residual term called 1/4 P2 sine square theta. So P1 square by 4 cos square theta plus P2 square by 4 cos sine square theta. 10 option B. So for 10, the correct answer is option B. So the correct answer is option B. So this concludes our assignment for week 5 on single sideband suppressed carrier and double single vestigial sideband. So I hope you enjoyed this problem solving session and we will meet again next week. Thank you.